All right, well, welcome everyone to the first in 2022 Zoom into Physics. This is Zoom 9. Let me start by acknowledging the traditional custodians of the land on which we're all meeting. For me, it's the Darug Nation here in DY, a beautiful suburb next to the sea that almost got washed away a few weeks ago. This event is organised by the Australian Institute of Physics, whose role is promoting physics into the community and industry and education, and promoting the role of physics in research. Tonight's topic is going to be very interesting. It's a question originally posted by Geraint Lewis that has gone really viral, and we'll get into that. So it's all about a video by Derek Muller, and who was one of Geraint's students, and he has become a YouTube phenomenon with, I think, something in the order of 11 million followers. And
sorry, I'm late, guys. I'm here now.
Hi. And the video that on electricity that we're going to be talking about has had something like 15 million views. And in the text for that video, you'll see that Derek acknowledges Geraint as the original poser of this question. So we're very blessed to have Geraint here to not only explain the question, but try and convince us why the answer is correct. There's always an opening question that we ask them to pontificate on as they introduce themselves. And tonight that question is, what was your initial answer to the question? And what was your reaction to the Veritasium video? So let's kick off with Tibor.
Well, thanks, Scott, and good evening, everyone. Quick introduction. I'm a philosopher of science from Sydney University. Well, my reaction was one of disbelief. It was contrary to what I was taught in school. Apparently, it's contrary to what everybody gets taught in school, which is quite amazing. I read up a bit on it, and lots of people are writing and complaining about how this is not what's taught at school. And so my reaction was just one of disbelief. I thought, I've got no idea what this is about, and I'm looking forward to Geraint explaining it to me in words of one syllable or less, please.
You're muted, Scott.
When I opened the chat and the chat covered the mute button. Sorry. Kirrily, while you've got the stage, please, over to you.
Thank you. So I'm Kirrily Rule, and I am an experimental neutron scattering physicist. I work at ANSTO, the Australian Nuclear Science and Technology Organisation. I have two hats on here tonight, though, because I'm also the National Secretary of the Australian Institute of Physics. So physics is, really important to me. And so when Geraint posed this question to me, I thought I had to, rip up my PhD, throw it out. I didn't know what was going on. Well, actually, when he first asked the question, my first thought was, well, if we have a wire, it doesn't matter how long it is, it's already full of electrons. So as soon as we close the switch, and electrons can start to move, it should be instantaneous. And so I think actually, Geraint, you can confirm, my first answer was probably the correct one, that it was almost instantaneous that the light would light up. But then, of course, we had Tibor and Scott weigh in with their answers, and then I got all confused and thought, I don't know what I'm talking about. I'll change my answer. So a bit of lack of confidence, and then watching the video, I got even more confused. So I've been doing a lot of reading up and a lot of trying to understand, but yes, I think we still need a better explanation, Geraint.
Thank you very much. Let's introduce our new member to the panel, Carrie Brenner.
Evening, everyone. Thank you for that introduction, and thank you for inviting me along. This is going to be a fun ride. I work at ANSTO with Kirrily. I lead the ANSTO's Centre for Accelerator Science, so that's another national user facility. But instead of neutrons, we are in the business of ions and ion beams. So we have 4 megavolt accelerators that are used for all different applications, covering radioisotope dating right through to irradiation and materials testing. So we've got a whole suite of different people that come through our doors all the time. My personal research background is actually high-powered lasers and laser plasma physics, and the connection to accelerators is that I use this laser plasma interaction, which is an very extreme version of an electric and magnetic field in the vicinity of electrons, as a miniature supercharged particle accelerator. So I design next generation particle accelerators using lasers. My current day job is to use solid state accelerators for lots of different applications, from environmental research and climate science to cultural heritage studies, right through to designing materials of the future for energy and quantum and space technologies. So quite a varied background, yeah, I'm looking forward to the conversation tonight. I've got to say, thanks for raising the question, actually starting this deep dive into kind of YouTube science communication or physics communication, because I don't tend to spend that much time on looking at the science YouTubers, but this has been a really interesting journey to see that there's quite a few different versions of this question that are out there now, and it's really interesting that some of the YouTubers have replied to each other as well through this question. So yeah, I think it was really good to have a deep dive into this question. I did not appreciate, Geraint, that's the connection with you and where the question came from, and that you had this connection to Veritasium. So I think that's what a wonderful, of this 1 degree of separation now from this like superstar YouTuber. It's just incredible. I had no idea that you could talk about physics and science and get 11 million followers. I mean, that's great for our community, and it's great that these questions are out there being asked and being talked about. So yeah, that's over from me for now.
Thank you, Carrie, and a very warm welcome to the Zoom into physics, and I hope you want to stick around for many more. So let's move on to the man himself, Geraint. Geraint, if you wouldn't mind introducing yourself and laying the groundwork about where this question came from and how it led to the video.
Hi, everybody. So I'm Geraint Lewis. I'm a professor of astrophysics at the University of Sydney, and I've been there for quite a while now. And that's how I've got my overlap with Derek Muller. He was a student. He did his PhD, not with me, but he did his PhD in physics education as part of the School of Physics. And of course, he's now gone on to found Veritasium and this very successful YouTube channel that he runs, where he addresses scientific questions. But of course, he doesn't just magically make up these questions out of nowhere. He actually talks to people and finds out what kind of interesting questions can he tackle, because of course the entire YouTube game is clicks, and clicks make money, etc. And that's how he supports himself these days, is by finding the interesting questions, getting in depth in there and providing those kind of answers to questions which on the face of it you might think that the answer is obvious, but when you think deeper you suddenly realize that things are a lot more complicated. So I've proposed several videos to him in the past. One of them was measuring the speed of light, the fact that you can't actually measure the one-way speed of light, it's always a two-way measurement, and that itself garnered millions of views and lots of shouting amongst people. But this particular video, which I must admit, the idea I came up with, I scribbled it out on a Saturday morning with a cup of coffee, and I scanned it and I sent it over to Derek and to one of his scriptwriters who's based here in Sydney. And I sort of said, what do you think about this as a kind of question? I didn't quite get it. I didn't expect it to explode in the way it did. And I must. Derek is in Sydney at the moment, and I was at a pub quiz with him last Tuesday, a week ago Tuesday, and you know, I think he's a little bit battle weary from the response to this, because there are those that I feel know the topic and sort of go, yes, that's how it works, and there are those that feel that they know the answer, which doesn't match with what Derek said, and are willing to fight for it. So that's the sort of potted history. My reaction, of course, when I actually watched the video was that this is an excellent video and the answer is correct.
Thank you very much. Now, why don't you describe the video and the question?
Okay, so let's describe the problem. So the problem is, of course, something that we often see in high school science, high school physics, where you have circuits, right? And you know, your simple circuit will have a battery in one place and a bulb in the other place, and you're told that, you know, the bulb is connected to the battery via a circuit, and when it's all connected, then electrons flow and the bulb lights up, and everybody goes, yes, that all makes sense, I understand that. The question that I posed to Derek was, well, we know that the battery contains energy, right? So we know that there's energy in the battery, that's why we buy them, we know that they run down, and we know that the bulb uses up energy. We know that the bulb turns energy into light, and so lights up. So how does the energy travel from the battery to the bulb? And of course, when you do your high school physics, you get analogies for the way that circuits work. And you know, one of the very popular ones is it's like a water conduit, right? So you have a bathtub and the water flows, and it turns a wheel, which is the bulb, and it flows. And then there's something that lifts the water back up, and that's what the battery does. And so it seems like a very obvious thing to say that the energy flows through the wires in the same way as the water flows through pipes or conduits, etc. So the way that I sort of expanded the question out is that I said, well, then let's make the wires really, really long. So what I'm going to do is I'm going to have the battery and the bulb separated by 1 meter, but let's stretch the wires out such that they're almost out to the distance of the moon. And quite clearly there, we then have to worry about the timescales for things to happen in the circuit. If you think that the energy flows through the wires in the same way as water flows through a pipe, then that energy has to flow through the wires, and that energy flow must be limited by the speed of light, because everything's limited by the speed of light. So you'd expect there to be a long time for energy to get from one place to the other. But of course, the answer in the video is that energy can actually cheat and jump the gap between the battery and the bulb. And I think that's the thing people find a little bit mysterious.
All right, can I throw in a question, Geraint? You said the battery contains energy. I suppose the question I would ask is, what does that actually mean? Because I know that if I have energy, it's not like I can have energy the way I can have a coin in my pocket or something. It's not that kind of having energy. So I understand the battery's energized. Yeah, I kind of get what that means. But what would physicists tell me about how a battery contains energy? What does it mean to have energy?
So going back to my first year electromagnetics courses, you get things to store energy when it takes you work to actually get, in this case, charges into a particular configuration. So that's how we talk about the way that energy is stored in this particular kind of system. So I've got a bunch of charges, and I'm going to take them and I'm going to squish them into this scenario. And it's going to take my muscle power or whatever way I'm going to charge the battery. And because of the properties of electromagnetism, that energy is a conservative quantity. That energy is then stored. So I can take the muscle work that I did to put into that configuration, I can release that at a later date. So in a battery, what we're talking about is that there's a charge separation, which is brought about by chemical reactions, and so that there is energy stored there. But I'm gonna caveat this immediately, right? Because energy is one of those words that we throw around in physics very easily, but when it comes to saying what energy is, things become a lot more complicated. So, you know, there's, if you asked any physicist to define what energy is, I'm sure you would get, you know, 1,000 different definitions of what energy means.
Okay, thanks for that. Your answer is actually quite helpful. I agree with you. I understand what you've just said, and that's what I understand energy to be as well. But it's interesting that on that interpretation, energy is not a substance, it's not a fluid, so it's not the kind of thing that would flow around in a pipe or in a circuit. So it already helps us to let go of this idea that energy has to somehow go through a pipe or go through a cable or a circuit or something to get around to the other side. Energy is now, as you say, it's an arrangement of things, but it's not actually something that has to flow from one thing to another. So you can let go of the whole flow idea now, can't we?
It can actually flow in some regards. If you were to have water going up in a pipe, then that would have potential energy. So, you know, these big towers and things like that where they store water. So that, I know that's not electricity, but so energy can flow. It can gain potential energy, and it can also gain kinetic energy when you have these hydro stations as well. But the other thing I was going to mention there, which I think helps what Geraint was saying, is if you have a Tesla coil, because a Tesla coil, you've got a very high voltage, and you can actually light up a fluorescent lamp with the Tesla coil. I've actually got one at home here, and you don't have any electrical sort of connections there to the fluorescent lamp. And in fact, I did one, I think, a while ago in physics in the pub, which you know which is what Tesla tried to do years ago. He tried to use it to light up a city without actually contact with wires and things.
But you've got to say whether it's DC or AC. You know, you can do that easier with AC. With DC, it'd be just a spike.
Sure, it's AC, the Tesla coil.
Yeah, that's right. But here we're using a battery. So it's when you switch it on, which is my question, is, okay, the light would go on, but does it immediately go off until all the rest of it kicks in?
So we're jumping in and assuming everyone has seen the video. So I just want to check whether that's true of everyone. So I don't know if you want to put your little handy up or whatever on the thing, but okay, it looks like most. Yeah, okay. There's a lot of people putting their hands up. There's a few who haven't. So let me launch the first poll I have. Hang on, yes. So the question is in the arrangement that Geraint described, what's the time period taken after you flick the switch for the light to come on? And so this is, the question is asking, honestly, when you first heard the question, and if you watch the Veritasium video, he asks you to pause the video and write it in the comments so that you can't cheat later. What did you think the answer was? I'm not allowed to vote, so I can just watch. Well, that's okay. 100% have answered. No, is that right? I think so. Let me end the poll and share the results. So, well, that's a pretty even across with not many with 2 seconds. My answer was 1 second initially. but I'm convinced of the right answer now, I think.
I certainly thought of it as Geraint mentioned it. It's sort of like fluid mechanics almost. You know, you're trying to get fluid through pipes. Well, if the pipe's already full of fluid, then it's already there to start with. But I think then watching the video and understanding that the energy comes outside the wire, that's something that's new with this pointing vector. But maybe I'm jumping ahead of the game here.
Yes, sorry, go, Chris.
Yes, it's new to me as well, but I've been thinking about it for a while, and I like the idea and it appealed to me. The only problem I have with it is how the energy is transferred from that magnetic field into light and heat in the light bulb. So with the idea of electrons traveling through a wire, the electrons are particles, and when there's current, they jiggle things around and make things hot inside the light bulb. So that's a transfer of electrical energy into heat energy, and then also into light. So I get it, I get that, but I have difficulty understanding how you transfer energy from the magnetic field directly into heat and light. I don't understand that.
I'm happy to jump in there if that's okay. So of course, if you've got an electron, it's charged, and so it will respond to the electric and magnetic field around it. And so what happens, of course, is that we know that electrons crash into things when they're in the filament of a wire, and that crashing into things, you know, heats up the metal, and the metal starts to glow, and that's how you get light. So the question is, at some level, what causes the electron to accelerate and crash into something? And it has to be the electric and magnetic fields. And what we've got in this particular situation is that the fields that the electrons in the bulb experienced aren't only because of the electrons behind it and the electrons in front of it, but are due to the electric and magnetic fields throughout the entire circuit, right? So it's not simply that the electrons get pushed by other electrons. They actually respond to the fact that things are changing in the circuit, and those changes propagate at the speed of light, which is why you get the 1/c answer that was in the video.
Also, you'll get a completely different answer if those wires were actually separated by that distance to the moon, because the electromagnetic field from the battery, from the inverse square law, is going to be so weak it's not going to have much effect on it. In fact, I guess the light globe itself is not going to give much. Is not going to light up very much at all. But it would take longer if the actual coil was separated. Instead of being 1 meter away from the battery, it was actually separated by a much larger distance.
Yeah, that's why we set it up to be 1 meter, is so that it would take 1/c.
So,
but
I was just going to say, Grant, while I'm there, is have they ever tried to put a dielectric between the battery and the light? So, in other words, you're really restricting the electromagnetic field, and see what happens on that one.
Yeah, you would get a different answer, but that wasn't the question that was posed, right?
Sure,
I mean,
sure.
If you want to mess around with the electromagnetic fields in other ways, then you get a different answer, but that's not surprising.
Carrie, you mentioned you do a lot of research in electromagnetics. Did this come to as a surprise to you?
Yes and no. So I think the answer isn't as it's a surprise. It follows my understanding and what I understand about electromagnetism and so on. I'm very used to applying that thinking about what happens to charges or charged particles in the vicinity of electric and magnetic fields. That's the background I come from, applied on a very extreme scale. I guess my surprise, I guess, was that the range of different interpretations that people have for what electricity is and electrical energy. And I think we're actually skirting around that a little bit now about the terminology, about what we mean by flow of energy, flow of electrons, then there's current, then there's electricity as a definition and what that means, and a carrier of energy, something that makes a change on something else and induces a transfer of energy from an electrical form to a light form, in terms of the light bulb example. And it was it's a grounding experience when you're a physicist working in physics all the time, and you spent the last X amount of years and decades of your life in physics and understanding these principles, but actually stepping outside the box and realizing that actually not everyone has the same understanding as you do is quite is an important experience. It's humbling, and I think it's something which all must do, because I think it's important to take people along the journey with us and find ways to describe these principles so that they don't seem so scary and mind-blowing. You know, what are we doing? I mean, what's happening in schools, or the way that we're teaching electricity, that we've all come up with slightly different interpretations of the same thing. So that so I got a little bit deep on the science communication and education side of things. I did really appreciate the illustrations. I think that's what you can call it, the diagrams, the electrical flow diagrams. It's something that's quite hard when you're starting to explain things, or with hands, in physical dimension that we work in. You got to start drawing things out to explain them. But yeah, I like that this was opening up the question about how energy flows, what it is, and what is the carrier in this place, and in this example. Yeah, so it did actually. I started asking a question myself: what do we mean by electricity? And now I understand, of course, when some people get the idea of flow of electrons like the flow of water through a pipe. But actually, in two ways, it's because there was something at the end of the video where he said it was actually nothing to do about what's going inside the wire. It's the energy's outside, which I appreciate, but it is actually something to do about what's going on inside as well, because without that initial movement or kick of the electrons inside the wire, you don't get the B fields, and there you don't get the transfer of energy. So we do have to be careful with the words that we use here, and then the descriptions, and we don't want to this is getting a bit deep. You don't want to upset and destroy people's belief systems in the world and the way around you by saying everything. I'm quite on board with the idea of saying everything you've learned at school is wrong. It's actually just that there's a deeper explanation about what's going on here, that unfortunately at the level of school, or that folks do not get exposed to, and that's such a shame. And that's it. So yeah.
Yeah, I think you hit the nail exactly on the head there, Ceri, is that as physicists, we start teaching children analogies of what we want them to understand. So we talk about, we've got a wire and we have this electron and it's a ball, and this electron is a ball, it travels in this direction, and that's how it carries the current, and that's how your light bulb lights up, and then everybody starts off with sort of something basic like that, an analogy again. But when we look into it in a deeper fashion, it gets a lot more complicated. And I think electromagnetism is brilliant in that it's always coupled. There's, if you want to measure magnetism in an electrical wire at your house, you probably could, yeah. So again, it's the analogies that we use to describe what we think is happening, what our observations are. I mean, is that all we do as physicists? We describe our observations with analogies to try and make it easier for people to understand. And does this lead to misconceptions? I've known many students to have misconceptions about physics because of the way they're initially taught with a simplistic model. Should we start with the difficult models or the more complicated, complex models at the beginning to avoid misconception, or are these simple analogies the best way to start?
Perhaps we can use words like. We can say things that this is like that. It's not really like that, but it's kind of like that. And you can think of it like this, but don't fall under the misapprehension that it actually is that. I think I think science education, particularly in junior schools, you're told everything as if they were facts, and you believe them as if they were facts, and then you go with it. And only later do you find out, well, okay, electrons aren't really particles, and electricity isn't really a fluid. And then you start working out that everything is different. Now, once you've worked in physics for decades, as some of you have, even I have worked in some, you realize that, and then you work out what the real answer is, and you work with it, and then you take it for granted that when you talk about particles, you don't really mean particles. And when you talk about energy, you don't really mean energy. And when you talk about mass, you don't really mean mass. And you don't have a problem with any of this. You can just work with it quite happily because you know what you mean and your colleagues know what you mean. But now you're speaking in a rather private jargon, which is known only to physicists. Everybody outside thinks that the words are meant to be interpreted literally as they were taught in school. And so they get the misunderstanding because they hear what you say, but they hear something completely different to what you meant when you said it.
The other thing I was just going to say there, I agree with what you're saying, Tibor, but it depends on the audience you have. If you're going to explain electricity to a 10-year-old, obviously you can't talk about electromagnetic fields and stuff. So there's a way of, you got to look at how you're going to explain something. It's a bit like when you explain atoms. I mean, almost everyone explains, that the atoms consist of the nucleus and the protons that moving around the atom. You're not going to be talking about, all these, more advanced sort of ways of looking at this stuff to a 10-year-old or something like that. But maybe if you've got someone in year 11 and 12, obviously, then that's a different situation. The other thing I would say is, electrons can actually move. They can move very, very fast, but not in a wire. If you get a lightning strike, then electricity can, the electrons can move very, very quickly. So electrons can move under some circumstances, but not much in a wire.
I've just noticed in the chat that we've got a message there from Peter, who said that he worked with Derek on the videos and wrote this video with Derek. So, hi Peter. Why don't you introduce yourself and tell us what's going on with part 2 of the video?
I've been dramatically creeping in the shadows. Basically, we're making a part 2, and we've been obsessed with this has given us a lot of grief. Like the last 2.5 months has been a lot of controversy from, lots of really, really clever people that, in the YouTube science communication scene and out of it that we really respect. And basically, Derek and I feel that we've been really tossing up whether we want to reopen this can of worms because it really feels like it's settled down a bit. But I think we've come to the decision that we weren't as convincing in the first video as we could have been or as we should have been. And yeah, we did an experiment, which kind of shows that what we're expecting to happen is the one on C answer. Of course, we didn't get, superconducting wire that went all the way to the moon. It was only 10 meters long, but that was still enough to measure the difference, right? So, and we also did a ton of simulations, and so, yeah, that's coming out. We need to finish the video, but I think it's coming out in about a week. And the big result for me is there are a ton of people who are arguing, yes, Veritasium, they're kind of right in theory, Derek's kind of right in theory, but as an electrical engineer, I will tell you that the amount of energy transferred across the gap is going to be so tiny that it's going to be insignificant, and you won't be able to light up, a light bulb or an LED or anything like that. And with the experiment that Derek did over in Caltech, which was a signal generator, right? Like we tried using a battery, but like the rise time on a battery, we basically couldn't get it to work where the rise time from the battery was quick enough. There was a signal generator and there was copper pipe that was separated like 3 meters above the ground, and it went 10 meters one way, 10 meters the other way. So, 20 total meters of pipe, and it was separated. There was an oscilloscope and there's the power generator, and the oscilloscope was a meter away. And we were able to get we're driving 20 volts and we got 4 volts across the oscilloscope within like 3.5 nanoseconds. Which checks out with the speed of light, which is exciting. We're not breaking causality. That's nice. And basically, I forget what the load, I think it was 1,000 ohms or 500 ohms across the oscilloscope was. But basically, we found a LED that basically was 16 milliwatts of power, right, within 3 nanoseconds. And at 16 milliwatts, there are small enough LEDs that do light up, right? So we were able to do that. So that's gonna be video 2, and we're gonna cause a lot more grief for us, but hopefully we'll be able to clear up a bunch of misconceptions from the first one.
Oh, good on you, Peter. I think all publicity is good publicity. So this is terrific for Veritasium.
I mean, there were 300
in any
emails
case,
today yelling that you're wrong. So
let me make one suggestion. One thing that I found that was missing from the first video, which is one of the reasons why it wasn't immediately convincing, was that you never said in the video that the amount of energy that gets across to light up the light globe is not the full voltage. You don't get the whole lot going over there. What you get over there is what is radiated across the gap. And I think if you cleared that up, if you said something about that, that might help. I don't know.
Geraint wants to argue the point, I think.
Okay, good. Go, Geraint.
Derek did set out his assumptions at the start, right? Like all good physics experiments. And there were 2 assumptions, right? Number 1 was that there is no resistance in the wires. So no energy is lost in the wires, right? So all energy just jumps the gap. And number 2 is that the bulb would light up with any current flowing through it. So in terms of that physics experiment, the answer is right. It wasn't a question of when will there be enough energy to light the light, because then you'd have to define how much energy that would have to be. It was essentially when would there be current flowing over there. So what I think a lot of people skip the assumptions without really, getting into the guts of that.
I heard the assumption, but I must admit that the implication was lost on me that the the LED would light immediately with any amount of current. I didn't quite think that through, and I think a lot of people missed that.
I do want to. I agree. I think that's a really good point. We could have made that clearer. Something that I do want to point out is that we didn't say any amount of current, right? Like when Geraint initially sent this email, I was like, okay, let me assume like any amount of current, like the light bulb will turn on instantaneously, right? That it's not an incandescent bulb. It doesn't need to warm up. It doesn't, as soon as current hits it, it lights up. But it's actually not any amount, because as a bunch of other people pointed out, there would be like leakage current across the switch, right? Like electrons will be just jumping across that gap, and there will be current always, right? Yeah. You could connect a battery on the other side of the world, and in the time that it takes, basically there's electromagnetic waves all the time, and if we said any current, then the light switch will never be off, right? Mm-hmm. Which makes the experiment super boring. But yeah, like it's actually it's a small, but it's a significant amount of current, right? As we did in the experiment, we got 20% almost instantaneously, right? And it rose from those 20% to 100. Whether that 100 will blow out that LED and break it, that's another matter, but we're physicists, so.
One of the questions that was raised in the chat of various websites and also in the video is, what role does the wire actually play? What if the wire was shorter, or what if the wire was not joined at the ends, or what if there was no wire? I mean, if the energy is leaping through space and going from the battery, if the battery starts to discharge and electrons move and a magnetic field is created and so on, if that's all you need, you don't really need to have, it's a decoy to say you've got this wire that goes halfway around the world, because it doesn't play any role at all. Or does it? Is it a case where the wires are antennae and you use the wire to transmit, like an antenna, to transmit the energy across the gap? Or is it something else that means the energy jumps across even if you didn't have the wire? What's the role of the wire?
Yeah, could we do an experiment where we just get rid of the wires and just have the magnetic field to light up the light bulb?
Well, you've got to create the magnetic field, so you've got to get electrons to move somehow.
Yeah.
I'm doing that experiment right now. I've got a packet of batteries over there, and I've got a torch in the other cupboard that's not switched on.
Works perfectly.
Yeah, is it a meter apart though?
So the thing that I couldn't understand is, and I understand, you know, and I think if I had to pick an answer, I'd pick the right one now, given on all the argument and convincing. There's something that just doesn't gel, and that's it. So if you put the switch at the far end, right, rather than a meter from the battery, what's the answer then? Is it the distance to the battery and the light bulb are still a meter apart, but the switch part is half a second away? Is the answer still 1/c?
I'm happy to answer that if I can.
Please do. Yeah, please do.
Yeah. So if are you saying you got your bulb and your battery, and then you got your wires and your switches over here, and you close the switch.
Yeah.
Then the light will come on with at a time which is the distance between the switch and the speed of light divided by c. So okay, can I go slightly deeper? Am I allowed? Okay, so nobody's mentioned it yet, but Graham's T-shirt. Graham, are you there? Can you?
Oh yes, yes.
Right.
Yeah.
Right.
Oh yes.
So Graham's T-shirt. Yeah, Graham's T-shirt has Maxwell's equations on it, and one of the best responses I saw to Derek's video was somebody who just said, "No, this can't happen." So they brought in an electrical engineer, and the electrical engineer said, "Yes, we do our electrical engineering stuff, but always, if you can, you go back to Maxwell's equations, because Maxwell's equations are what govern electricity, magnetism, charges, and currents. They are the classical laws of how those things behave. So when you talk about electricity and you talk about, you know, V equals IR and I squared R, or whatever the rules are, etc., they're approximations of what Maxwell's equations would tell you is happening in the universe. And so what you have got is that when you have any particular setup where you have a circuit and you've put a battery into a circuit and the circuit is open, even though you think the battery is here and the light bulb is there, because your battery creates an electric field, all of the electrons in the circuit know about the existence of the battery, right? They shuffle around, even if it's only by a little bit, because there's electric fields there. So when you close the switch, what you're doing is you're changing the electromagnetic sort of configuration, and the information of that change propagates through the situation, and that propagation is in the electromagnetic fields, and they propagate at the speed of light. So if you're going to change something somewhere, then it's going to be the distance divided by the speed of light somewhere else, that something's going to respond to that. And that's basically what the idea behind my question eventually was.
Okay.
That doesn't quite answer what Scott was saying. So you're still saying it's 1/c. But,
no,
but
it's
then,
the distance
okay,
between the
yes.
switch on
Okay,
C.
now I just wasn't sure.
So,
Now the interesting thing on that.
Yeah, go ahead.
It's just that it would first go on when you were just setting the stuff up and you're putting the wire onto the battery, and then you'd get a spike, and then you could go and do your experiment, right? I was going to have a question and a kind of part of an answer to what would happen when you look at the magnetic fields here, because you're going to have a current that is going to loop back on itself on parallel wires. And we know that parallel wires where there are contradictory directions of current will move apart. So if you had your experiment floating in space and you switched the switch, the light and the battery would go apart, and then I gather a ripple until the whole thing was kind of, I don't know, some circle or something. Just like when you have currents going in parallel wires the same direction, that they come in together.
Yeah, but you're just adding complicated factors. You have to remember I'm an astronomer.
I know
so
that.
Everything's a spherical cow.
I know that, but it was just interesting to say if you had this set up floating in space, you'd actually have to take into account that the distance would change between the battery and the light because of the magnetic fields would push them apart.
Right.
So historically, this is to do with Oliver Heaviside, is it not? All this question, yeah.
Graham, I want to know if your T-shirt will light up a light globe.
Well, as I thought I might have been on mute. As I mentioned before, and I did the physics in the pub, although I had a baby Tesla coil. At home here, I have a 300,000 volt Tesla coil, and I can assure you that it lights up fluorescent lights up to 10 meters away from the source. So it gives it in every direction. So as Grant was saying there, you have a coil and it's giving an electromagnetic field in every direction. Obviously, it's the inverse square law attached to it. But a fluorescent light doesn't need much current to actually glow, whereas if you had a light globe, then obviously you're not going to light up a light globe very easily unless you have a much more powerful one. So
one of the just to add to that, one of the things that we did as well is to convince people that fields are important. Is we got an argon tube, right, with a cathode and an anode, right, and actually that doesn't really matter. And we put it next to a Van de Graaff generator, right? So it's DC, right? And if you keep it steady, right, nothing happens. It doesn't light up. But we attached it to, a ruler and put some wires on it, put some string on it, and then we spun it around. And you can see that as it spun, it actually discharged, and discharged, which I thought was really cool. It didn't. We filmed it before the first video, and it didn't quite make it in. But yeah.
Well, I just have to say I'm really excited about the second video coming out. In some of the, as I was saying in my first few comments, some of the, this has been a bit of a journey for me, as in exploring how science and physics is described on places like YouTube, which is at the moment one of the primary ways that people who are not in the business or profession of physics get the information about science and get an interest in how they find out about what we do. It's a really, really important platform for communicating the excitement and the mystery and the awe of the subject that we have all made our careers out of. And I think this is really important that actually we do keep on spreading this message. Yes, it's going to start asking questions and people are not going to be, maybe they won't be convinced, but that's why we need to try harder. We need to try harder on how we describe things to people without relying on maths, without relying on the comfort of our textbooks and our complicated language and our complicated equations. We really need to find a better way to invite people into this wonderful world that we inhabit of physics. I think it's really important that we continue doing that, actually finding these visible observational activities, experiments that people can see and take part in, rather than having just to rely and trust on what people say on a video, because we also know that's the downside of kind of the internet and the freedom of it, is that information can go out there that isn't aligned to our observations and our truth, whatever that is. Let's also get people being uncomfortable, getting comfortable with being uncomfortable. Isn't that what got us in physics in the first place? The fact that there are still so many questions to ask, and that's a great thing. If we knew all the answers, we'd all be out of a job. right? That's research, and science is all about, is constantly asking questions that have never been asked before. And so I think it's really important that we do find a way to talk about fields, describing what fields are to people without people having to get a degree or qualifications in order to then be welcome into this secret club of physics. Why is it so secret? Like, I honestly, like, I think that in all the kind of science communication and physics communication I've done in the past, that's one of the things I've always tried to get through is this, I think, is a huge barrier to getting more people into our profession, getting more people signed up and active in physics, is that it's often seen as a very exclusive members club, and that's our loss. So
yeah, you're absolutely right, Ceri. I couldn't agree more. But I think it ultimately falls to us scientists to communicate the science and to educate people, but to communicate to them at the level that they understand, not to communicate to them at the level that we understand, because we can be talking cryptic physics and no one will understand what we're saying. So we have to get out there and spell it out to them and demonstrate and illustrate and explain and describe and stand on our heads and wave our arms about and do whatever else it takes to get people to get a handle on some of what we want them to understand, or we would like them to understand. And I think there's an issue here that goes a bit deeper than this. There is generally, I think, in the population at large, and I'm guessing, I don't know the percentages, that there is a general mistrust of science, which is largely because people just don't understand what we're doing. If we were able to communicate science better and people were even marginally more scientifically literate, I would wager that there's going to be less anti-vaccine and less climate change denial and less of these other things, because people will start to understand that there's something in this, that there's something to get a hold of. So in a way, the science movement does itself a disservice by not communicating the science to the general public. And of course, you also want the general public to fund all your efforts through government funding and wherever else the money comes from. So if you want the public on side, I think that one of the first things that we have to do is actually to communicate our science, and we're not doing it terribly well. If the evidence is that you get debates like this hysteria that now surrounds that Veritasium video, it's comical. But if that's the result, then that's a clear indication that we're not communicating science terribly effectively.
One thing that you can say about this video is it's got 15 million views. So I mean, so you know, maybe Peter can comment why is this so successful? Because, you know, I mean, getting the message is good, but getting it so that it's as viral as puppies and kittens is you know, what's the secret to that? I mean, Veritasium's found that secret, but what is it?
Oh man, I wish we found that secret. We just launched a video today that is not doing well by our standards, and we thought this would hit, right? Spent the last 3 weeks just like full blast working on it, and it's just like not doing as well. I think there's a lot of factors, but like when it comes down to it, it's actually relatively simple, which is you need to make stuff that people want to watch, right? And then you also need to make sure that people click on your video. So it's really important to take an interesting and surprising and intellectually satisfying, relevant and never seen before, you know, like those kind of topics are really good. Those are kind of our criteria, like that's our mental checklist that we do. It's like, hey, is this video, should we, you know, sink hundreds of hours into this video? But ultimately it comes down to finding the 50 characters in a single image that, you know, makes a person click on a video like this video instead of, you know, cats running around or whatever else is on YouTube, right? And that's really hard. And I think one of the reason that there's been so much controversy about this video is actually the reason that it's been successful, is because it is surprising. It is counterintuitive. This is not the main bit of the video, but I love this part, is when you describe the pointing vector for the first time, right? And we go, okay, so the pointing vector, you know, you have your E field doing this, and your B field is doing this, and here's your laser pointer, and you point the laser that way, and the energy transfer is, you know, in the direction of the propagation of the laser beam. Like, makes perfect sense, right? You're like, great, the pointing vector is great, I totally understand it. You do the same thing for a really simple circuit, and you realize that the energy from a battery isn't coming out along the wire, it's coming radially out in all directions, right? And like, yes, the wire does end up curving it in, and it actually sticks relatively close to the wire in the real world, right? And the same thing for the battery or a resistor or whatever, and it goes radially in theoretically from all directions, right? So I just love that. Here's this really simple idea, right? Here's this really simple concept that seems to make sense for one case, and then you apply it, and all your intuitions go out the window. You're like, this can't be right, right? So yeah, finding things that are surprising and hopefully telling the stories relatively well. Yeah.
I've got a question, again, slightly out of left field. I remember seeing a video by Robert Lewin on gyroscopes. He brought a great big gyroscope into the room and spun it around and then did all sorts of funny things, because they also behave in a peculiar way. They spin one way and you try and turn it and it sends you off sideways. It also has a similar kind of counterintuitive effect. And it's just as interesting. I would suggest that might be something Veritasium might like to do a video on as well.
There's a whole series about 8 years ago that Derek did.
But my question is, could the two mechanisms, whatever they are, be somehow related? The fact that the pointing vector goes off sideways because the waves go this way and the fields go that way and so on. Could that be somehow parallel to the kind of thing that goes on in a gyroscope? Because that also tends to do things sideways in a funny way. Is there some sort of parallel in, I don't know, in the mathematics or something that it's the same?
I think they're completely different.
I'll just jump in and just say that all of this, it's vector cross products. That's what does it for you. When something goes off in a strange direction, it's a vector cross product. And for magnetic fields, you get vector cross products, and pointing vector is a vector cross product. And angular momentum, you get cross products as well.
Okay,
great. You just blew my mind. That's amazing.
But I'm going to clarify that by saying that I am not a fan of vector cross products. I think that we're being misled by them, but that's another story.
The thing I was going to say there, thanks Peter for what you talk about video, is you need to sort of work out what sort of audience you want as well for the thing. So people have probably been through school and taught electricity a certain way or have an interest in that. You want to target that sort of audience, and then you get what sort of, you know, probably get a large number there. I'll say one other thing there is, in some of those ones like Peter, your videos and things, is you actually have some sort of idea, and then you ask people what you think is going to happen. Now, there are some circumstances where no one knows what's going to happen. Something very, very simple, as has happened a number of times in the past, where no one knows what's going to happen unless you do an experiment. And the classical one is having a candle. And a candle on Earth has a flame of a certain size, and you put a candle weightlessness, say, on the space shuttle, pretty much weightless. What's going to happen to the candle? Does it go brighter? Or does it go out? This and that. Scientists were talking about that for a long period of time. It's a very simple thing in theory, but no one knew exactly, weren't sure what was going to happen until they actually did the experiment on the International Space Station, and they actually got a result for that. So some of these things you don't actually know what's going to happen until you actually perform an experiment.
One interesting thing about fields is the fact that any body in space, like the Earth, has an electric field around it. And so if you tell people that, here's a warning, if you're drowning at sea and a helicopter comes to pick you up and they drop a bucket on a chain down to you in the water, be sure to let the bucket touch the water before you touch that bucket, because it will be at a high voltage if it's still dangling in the air and you reach out to get it. So those sort of things are really quite good. And I find it happens at home because I have an antenna on the second floor. And if you just touch the antenna wire, you get a little tingle out of it. And I gather that's the potential between me at the floor level and the antenna, the TV antenna way up on the chimney.
That reminds me of an experiment that was done in the 1980s on the space shuttle. It was an Italian project, I think, where they had a second satellite, and it was tethered to the space shuttle, and they were going to unwind it 30 kilometers outwards in radius. So it was cutting through the Earth's magnetic field, and they thought, oh, maybe we could put this on a space station to generate current, right? Because you've got a wire moving through a magnetic field. And they unwound it 500 meters, etc. And the current got so high that the cable burnt out and the satellite snapped, the cable snapped and it floated off into space. So,
Wow.
people have tried to tap that kind of energy. There's a lot of it there.
Yeah, I read somewhere there's something like about 300,000 volts between the ground and upper atmospheric clouds or something. It's huge.
One thing that came up in
Between your nose and the floor.
the videos as well was about the flow of energy, and it was that the only thing that was important was conservation of energy, and the energy goes out into the field and then it gets sucked in from the field. But so is it, and it did, I think that the comment that was made in the video, it doesn't have to be the same energy, whatever that means. Is that is it so that there's an amount of energy out there, and you can add to it and subtract to it as long as you do it in equal measures? Is there anything to that argument, or is it complete bunkum?
No, I mean, that's completely the right argument, isn't it?
Okay.
In that, you're so I'm sitting here in this tiny office I'm in, and I'm surrounded by electric and magnetic fields, right? Because there's cables and wires and everything everywhere, and the earth. And in my hand, I've got electric and magnetic field, but I can't distinguish, is this electric field from the earth or that wire or the monitor, etc. So it's just there. And if I have a device there that could tap into that energy, it just taps whatever electromagnetic field is around it. So yes, but to describe this entire situation, of course, I would need to think about all of the currents, all of the charges, all of the fields to ask about what energy is at this particular point.
I just think that's like beautiful. Isn't that beautiful about the world that we live in? This idea that the energy is the total value of energy everywhere is just a constant, that life and everything, the being, the world is just actually a constant transfer from one type to another all the time. And that's the goal of what a lot of physics is understanding what types of energy are, what descriptions fit those energy types, and tracking how those energy forms or types change from one form to another and have an effect and do something that can be observed. I actually think it's quite I find it quite a comforting theorem about the conservation of energy. It's something quite beautiful when you think about living in this universe or this situation that we're in. I think it's really nice. But yeah, I think we shouldn't shy away from describing what those types of energy types of and what the types of really are. That's one thing, coming back to the idea of electric and magnetic fields, they scare people because it's hard to interact with them ourselves. It's not like other types of energy which you could probably either see and observe or feel. That I think, that's why people are not so, maybe a bit more afraid of it. Is that it, or we're just not? Again, does it come back that we're not doing a good enough job explaining what that is?
I think if often, as you said, with the electric magnetic fields, they feel a bit ghostly, right?
Mm.
They're there, they're in the room with you, but you can't see them, you can't feel them, but your devices are working because of them. I definitely agree with you about the beauty of this notion of energy and energy flow. And of course, thermodynamics is probably going to be for a separate day here, but of course, that flow, which is life, is also tied to life, is also tied to entropy and decay and all that kind of stuff. So it rapidly heads into the philosophical kind of questions about life and meaning and what's going to happen in the long run.
Yeah, I want to add to that discussion that fields are all around you, but it's difficult to feel them or know that they're there. And as part of my job, I work with high magnetic fields, and so I have a device here, a little gimbal, which is like a little compass that detects magnetic fields, because stray magnetic fields are not so great for the work that I do. And this is one of the best things I have, and one of the best toys I have to play with, because if I have a magnet, I don't know if you can see this, but I come up and I can sort of trace the magnetic field lines. I don't know if you can see that. It's moving around, and it's just I can even feel the force on this gimbal as I get close to stray magnetic fields. And it's a wake-up call or an amazing realization about how strong these fields are that are surrounding us. And if we don't measure them or observe them, you just don't know they're there. I mean, that comes for so many different things, be it, magnetic fields or even radiation. You don't typically see radiation around you, but, we have devices to measure radiation. It's important. Yeah, anyway, I just had this little lovely device that is one of my favorite toys at work anyway.
There are lots of things that go on around us for which we as human beings don't have detectors. We just don't detect those things.
I do. I'm just going to say, Tibor, because Kirrily's talking about, I've got a little device here as well.
Move it in front of your chest.
Electromagnetic fields, and it picks up wires and all sorts of things. If you can't find a wire in your side of your house, this thing's probably got a flat battery now, but yeah, it's called Dr. Gauss, which I actually got from the United States a number of years ago and actually put it together. So this thing here is actually quite good in a workplace. I remember there's one guy I worked with, and he actually worked at a place where they had all the servers and stuff, and then the electromagnetic field in there was actually higher than what was supposed to be by OH&S, and depends how many hours you're working there, of course, but yeah, you can get little devices like that, which are actually quite nice.
Yep. All right, so back to my earlier question, Geraint, I didn't get an answer from you about what is the role of the wire. What does the wire do in the experiment that we're talking about?
What does the wire do? For the purposes of this experiment, the wire is there to give you something for currents to move in and generate electric and magnetic fields. And one of the things that I spoke with Peter and Derek about, of course, is that one of the famous experiments from more than 100 years ago now was, an Italian Marconi taking a piece of wire and, causing a current to go back and forth in that wire. And that caused the current to move in a wire somewhere else, right? So, that was the discovery of transmission by radio waves, but it's exactly the same situation. You just need some way to control your currents to get your electric magnetic fields. Now, if I was smart enough, and I'm not, to do plasma physics, right? In plasma physics, where you've got currents all over the place and charges all over the place, you have to worry about all of that kind of effect throughout your plasmas. So, for us on Earth, we want simple circuits where we could control where the electrons are and how they're moving. And what we have is the simple circuits to do it.
Okay, so if the wires were not joined, were disconnected at the ends, halfway to the moon and halfway out the other way, if the wires didn't join up, the light would still light up, and shouldn't make any difference until such time as the voltage across the wire or the current stabilized, it reached some sort of equilibrium, at which point the current would stop and then you wouldn't have any more effect. Is that correct?
Precisely, yeah. So once you've got to your new steady state, then everything just settles back down again.
Right, okay.
And again, there's several videos from transmission line experts responding to Derek's original video. And again, they said yes. You know, then you can go into all kinds of language about impedance matching and all this kind of stuff. It's all Maxwell's equations at the bottom. Speed of light matters. That's the thing that controls when things respond to when things change.
One of my favorite things that, like, we've learned a ton of things from making these videos. Yeah, it's been great. Like, it's been so fun to learn all of this. But one of the ways that electrical engineers like to talk about circuits is what's with the lumped component model, right? So they kind of try to ignore the fields as much as they can, and they replace the fields with capacitors and inductors that would do the same thing. So what you can do is you have two parallel, if you have two wires running across it, how you can model it, how an electrical engineer would model it, right, is by putting, so you'd have resistors running along the lines. We don't have any of those because, you know, superconducting wires. You end up putting small, like, capacitors just across that, right? So in the you know, a nanosecond immediately after we close the switch, there's like this tiny little circuit with a little bit of wire here, a little bit of wire here, and a capacitor, right? And that's how you know, how an electrical engineer would talk about the current getting through. And then, like, the capacitors move and move and move, and you end up, you know, completing the full circuit. But it's really interesting that, you know, like, in this language of electrical engineering, it's easier for them just to not think about the field, right? It all comes down to Maxwell's equations, but, like, the language that we use, right? Yeah, I thought that was really cool. If we model it that way, we modeled with the full field thing, right? We have beautiful pointing vectors doing exactly what we expect them to do. And we also plugged it into, I forgot what it's called, ANSYS? It's like an electrical engineering simulation thing, right? And we got, like, the exact same result with the lumped, you know, the capacitors running across the transmission lines. So that was really fun.
I actually saw a calculation a while ago, I vaguely remember it, where they try to work out the best way to get close to a decent fraction of the speed of light. Excuse me. And the way that was envisaged was to get a metal spaceship, have it in orbit around Jupiter, which has got the strongest magnetic field around, and it absorbs the energy and it gets transferred to speed, so it gets faster and faster. But obviously, if it's getting faster and faster to stay in orbit, it's got to get closer and closer to, it's got to get lower and lower, and eventually it's going to, you know, run into the atmosphere or something like that. But that, they actually worked out you can get up to about 5% the speed of light on a theoretical basis anyway.
Okay. Well, I think Kerry's right, actually. I think that the lesson I learned from the video and from the question and that was that my understanding of how electricity works, even though I knew about pointing vectors, was still not visceral. I still really didn't get it. And it's something that goes back to what Kerry said. I don't think we're communicating these things terribly effectively. I mean, I went through high school and did physics and went to university and studied physics, and I came out and I still got the answer wrong. So clearly I wasn't taught terribly well, or I didn't learn terribly well. It might be my fault. But there's something in science communication which is lacking somehow. I'm all for lifting that game. I'm a strong advocate for improving that.
And things are certainly improving, aren't they? Especially with all these YouTube videos. I mean, you know, I was asked the other day, actually, my son was saying to me, who's your favorite YouTuber? And I was, well, I can't think, but it has to be a physicist, doesn't it? Because they're the ones that are describing and explaining the things visually. I mean, we're very visual people. If you give me a maths equation, I have to sit down and really think about it hard to work it out. If you show me a GIF or a drawing or a motion of something, you know, it makes it a lot easier for me to sort of conceptualize in my own head what's going on without someone saying an electron is a ball and it travels through a wire. You know, perhaps we need to take a step back and look at our elementary school kids, our primary school kids, and not talk down to them. Tell them about this, pointing vectors. Tell them how electricity and magnetism are linked so inextricably. You know, their minds are open to these things. Perhaps it's only as we get older, after we've learnt all these, you know, simplistic analogies, that it becomes harder for us to go back and relearn, you know, what might actually be going on.
That's true there, Kirrily, but I think what should go with that is demonstrations, because people, audiences and stuff love demonstrations. So if you're actually getting your point across by doing a demonstration, and then, you know, like with the Tesla coil, physics and power, I have done a number of these in schools, and they are fascinated, where you have a piece of metal, you know, in some water, and you've got a ping pong ball in the water, and you challenge someone to try to get the ping pong ball out of the water, and it's not touching the chain into the water, and they get a nice, decent shock, you know, and they can learn about electricity that way. The other thing is, a lot of people learn stuff, but they don't really try to understand the stuff. They just learn rules and this and that. You know, V equals IR. The most common equation that everyone knows in the world probably is E equals mc squared. So if you were to ask someone what that actually means, you know, they probably couldn't tell you. They wouldn't even know that the M's are mass. And see, it's sort of like Edith wants you to buy 2 kilograms of mozzarella cheese, that sort of thing.
I just put a link in the chat. I know we're coming to the end here, but this might be a topic for another discussion. I have discussions with some of the guys that are involved in like HSC physics. So there's high school physics and Simon Crook's Crooked Physics. And we have this discussion all the time about what kids should be taught. And there's a strong feeling from his side that, you know, you need age appropriate material. Right? I guess you can't jump into Lagrangian and Hamilton mechanics when they're in kindergarten. But we are we also have this constant discussion that what happens when people get to university is that we spend quite a chunk of our time fixing the myths and misconceptions that come through with regards to what was taught at high school. And one of my big discussions of the last 2 weeks is this claim, and St. Patrick's Day did it, that the sun is really green. That, you know, so and it's to do with a complete misunderstanding of the black body spectrum and all this other stuff that people have seen, but they don't quite understand. So maybe we'll save that for a different discussion, a bigger discussion about science education.
And misconceptions and how to clear them up earlier.
Yeah.
Good idea.
That's a great one.
I think that's probably a good place to end for tonight.
Sorry, Sam.
Yes?
Sorry, just one more point, of course.
Yep.
One thing we didn't mention, we've spoken about the pointing vector and how it's the direction of energy flows. We have to point out that was named after a man called Poynting. So was it nominative determinism? That he had an ideal name. So if you're going to have a scientific law named after you, either be called dielectric or something, right? So you can have a good name that works.
See, I have to come up with a rule, and then I can call it rules rule.
That's right. Yeah. Mm-hmm.
Yes, I think I've worked out what the solution here is. We need to get Chris Ferry to write a new book called Pointing Vectors for Babies, and then we can start off with all of this very, very early. Geraint, you made the comment that you need to be really smart to do plasma physics, and so I can let everyone know tonight that we're actually going to be doing plasma physics at the next Zoom into physics. I'm very happy that we will have an ex-colleague of mine join, Dr. John Loki. He's been a plasma physicist with CSIR for many, but he's actually an expert. He's been on ball lightning, and you know, to the extent that he's come up with some theories of it, and tried to create ball lightning in the National Measurement Institute's high voltage lab, which was pretty cool. So I'm very pleased to have him next week. And so the topic is going to be, what is ball lightning? There are plenty of very credible observations of it on the ground and in aircraft and so forth. But we still can't really explain it. And so we'll have a good old chat about ball lightning next time. So in closing, can I just thank our 4 panelists very much for joining us again. And thank you very much for a very stimulating conversation, everyone. Okay, so thank you very much, everyone, and see you next month.
Great stuff. Thanks, everyone.
Good night.
Bye.